Hey everyone, now that we've cleared the specific integration techniques, we move on to the more general techniques, and we start off with integration by substitution. In the syllabus, you'll be given the substitution, although with enough experience and practice, you realize that there are many common substitutions. So what's integration by substitution? Well, let's start off with an example, integrating root 1 minus x squared dx. Alright. Clearly, you can't use the power rule because you'll be introducing the new variable term x, because the derivative of the function inside the bracket is x, 2x actually to be more specific. So, you cannot introduce a new variable term in your integral, and therefore it is invalid. And there's no other derivative that is root 1 minus x squared, so there's no direct function that gives us the integral. As such, one way to do it is that we substitute x as another function. So don't worry, in the exams for the H2 math syllabus, you'll be given the substitution. But if the case where they tell you to find the other method, so like example, hence or otherwise, you are allowed to use the substitution method if you know, but in that case, they won't really give you. But most of the time, if they want you to use integration by substitution, they will give you the substitution. So from here, the substitution would be x equals to sine u. Alright, and we have to restrict this further. Let's say u is between 0 and pi over 2 inclusive. Alright, so now we put in the substitution, we get root 1 minus sine square u. Now what's the problem? We cannot integrate with respect to x anymore, right? Because there's no x variable in the new function that we're going to integrate, because we've just substituted x with u. So we kind of have to integrate with respect to u, right? So du. But we cannot just simply change the variable from x to u, because x is now a function in u. So what do we do? So here's the thing. The trick is that after you make your substitution, you must multiply by the derivative of the substitution, dx du. One way to remember this is that, well, dx, right? So we have dx, kind of like fraction, dx over du times du, and then you cancel this out together. But please don't add in the times here, it's actually illegal. That's why I don't put in the times here, but you can think of it this way. So we know that dx du, so we have x equals to sine u, dx du in this case would be cosine u. So what we do is we have cosine u times root 1 minus sine square u, so 1 minus sine square u equals to cosine square u, if you remember your identity relationship for trigo. So what's the problem here? Here comes the second problem. When we have root a square, the answer is actually a dependent function. It's a piecewise function. It's equals to a if a is bigger than or equals to 0. It's equals to minus a if a is less than or equals to 0, because any positive square root would give a positive number, but a might be a positive or negative number, right? So this is why we have to check whether a is positive or not. So we go back to the question. What did the question say? U is between 0 and pi over 2, which means that sine u is in the first quadrant. And we know that in the first quadrant, all trigonometries are positive. As such, we know that cosine u would be positive. Because of that, we are able to have cosine square u du instead of minus cosine square u, or neither do we have cosine u times modulus cosine u, because of this range. So this is the first technique that you need to know. One is to multiply by the derivative of the new substitution. The other is to check the range of your substitution. So if you recall, right, we cannot integrate cosine square u directly. We have to express it through the double angle formula, which would be integrating cosine 2u plus 1 over 2 du. And then what we will have is sine 2u over 4 plus half u plus c. We are not done yet, because we now have to replace our x back, right? So here comes the thing. We know that x equals to sine u. Alright, we can express u in terms of x, right? U equals to sine inverse x. So we solve the first part, right? We have half u. But what about sine 2u? So sine 2u, now what? We have x equals sine u, but what can we do? Well, go back to the basics. Sine 2u equals to 2 sine u times cosine u. Alright, so we have basically 2x times cosine u. What do? We don't have cosine u, but we can find cosine u, right? We have x equals to sine u. Cosine u is basically, well, through the identity function. So we know that if we have 1 minus x squared equals to 1 minus sine square u, it will equals to cosine square u. You take the square root, so you get cosine u equals to root 1 minus sine square. Therefore, we have this, we have x root 1 minus x squared over 2, because sine 2u is 2x root 1 minus x squared, so 2 over 4 is half, plus half sine inverse x plus c. And this is integration by substitution. Alright. I'm now going to prove why we have to multiply by the derivative of the new function. So if you are not interested in the proof, well, no worries about that. You don't actually have to know this proof. But the main thing is that the steps to integration by substitution is as follows. Number 1, substitute first. Okay. Number 2, multiply by the derivative of the new function. And what is a derivative? Now, there's a few ways to think about it. So let's say I first have, let me use another color. Let's say I first have fx dx, right? Now I substitute, let's say x equals to fu, alright? Okay, maybe not, let's not use the word f, right? Gu, okay? Then after making the substitution, you would then obtain f bracket g bracket u. Okay, I have to write that down, right? So multiply by the derivative of the new function, which means that you want to multiply by dx du. Okay, how do you remember, is it dx du or is it du dx? Very simple. Ultimately, you want to obtain the following integral, right? Where you have a function, let's say after integrating you get hu du, right? Now, at first you have dx, at the end you have du. So at first is on top, at last is below. So you have dx on top, du at the end, therefore dx over du. That is how I remember it. Okay, so first step is substitute x gu, then you multiply by the new function, so you get hu dx du, and then you can integrate it afterwards. So what is the proof that you have to actually multiply by the derivative of the new function? Here we go. Let's say I have an integral fx dx, right? I have a substitution, let's say I have a substitution x equals to gu, using by the same examples here. So I therefore have f gu, then d gu. Okay, so I integrate with respect to the function gu. What do I get? So I would get the antiderivative, right? So capital F gu plus c, of course. Now, then what do I do with this f gu? Because I wanted to find the integral with respect to u, I would differentiate this with respect to du. And I would get f gu multiplied by my derivative of dgu du, which would then be g prime u. I have to differentiate outside and then differentiate inside. So I differentiate capital F to give me my small letter f, and I differentiate inside gu to give me g prime u. Because of this, if I were to integrate this now, so I get back, if I integrate d f prime u du, I will get back basically fx, right? Or capital F x. So if I integrate this, I know this with respect to du, then if you notice, it's basically g prime u is the derivative of the new function here, which is basically dx du du. And from here, we then have integral fx dx. Alright, so this is the proof of the integration by substitution, and this is generally just a simple technique.